Welcome to qnawire.
For this problem, the first thing that we want to do in both part A and part B is going to be to find our critical z-score for our hypothesis test. Now, we know that we're doing a right-tailed test at alpha equals 0.05, so the critical z-score is going to be z for a right-tailed proportion of 0.05. I'll find that from my table of values over here. We want one tail 0.05. Come down here, evaluate it, we can see, or I'm not evaluating it, but down here for the z row, we can see it's 1.645. Then what we need to do is use that critical value to figure out what the critical value of the sample proportion would be. So we have that the sample proportion corresponding to that critical value, which I'll call p hat c, is going to be equal to our null hypothesized population proportion plus that critical z-score times the square root of p naught times 1 minus p naught divided by n. So let's see here. We have our null hypothesized proportion is 0.15, then we do plus 1.645 times the square root of 0.15 times 0.85 divided by n, which is 133. So we have that the critical proportion is going to be 0.2009. Now that we have that, for part A, we're looking for the probability of getting a sample proportion greater than 0.2009, given that the population proportion is actually equal to 0.16. So our first step is going to be to figure out the z-score for that critical proportion when p is actually 0.16 rather than 0.15. So we calculate that by taking 0.2009 minus 0.16 divided by square root of 0.16 times 1 minus 0.16, which would be 0.84, divided by 133. So this is going to be equal to the proportion of z to the right of roughly 1.29. Oops, 1.29. Now I'll find that using a cumulative distribution table, where I'll note that the proportion to the right of positive 1.29 is the same as the proportion to the left of negative 1.29. So I can use my table of values here and see that it's going to be 0.0985. And then for part B, we do basically the same thing, only we change what we assume we change what our condition statement is. We change what, I just realized I have made a slight mistake here. What I calculated there was the power, but we are being asked for the beta. Beta is the probability of a false negative, and I calculated the probability of a true negative, or a true positive rather. So to get the actual beta value, it's just 1 minus the probability that I calculated. So it's 1 minus 0.0985. So for part A, the beta value actually should be 0.9015, pardon me. And then continuing on for part B, we can see that actually if we wanted to get beta, it would be probability of a sample proportion less than or equal to 0.2009. In other words, probability of not being in the critical region, given that p is actually 0.21. So again, we calculate a z-score and get the probability. The z-score is 0.2009 minus 0.21 divided by square root of 0.21 times 1 minus 0.21 divided by, the sample size, 133. So this is going to be the proportion of the standard normal distribution to the left of roughly negative 0.26. Which I'll find using my cumulative distribution table again. Only now we want proportion to the left of negative 0.26 rather than proportion to the right of a positive, but it doesn't really make too much of a difference with how we use the table. All right, so we find that our beta is going to be 0.3974.